Okay, following on now from what we learnt about radians in the last screencast, and the usefulness of using radians as a measure as opposed to degrees, and just the purity of it and the logic of it. And so what I want you to take out of that is that now radians are going to be the way forward for us. And so let's start thinking in terms of radians. Radians need to become second nature to us, just like degrees are now. Right, so let's start with pi and 180. That's the conversion. That's the sort of the base conversion. 2 pi 360, pi over 290 go both ways. Right, we're going to start using radians now. I'm going to show you how powerful, how easy they make some of our calculations. And we're going to start by looking at the arc length and area of a sector. Now, a sector is a sector of a circle is one of these. That's a sector of a circle right there. Right, it's just a it's a piece of pie. That's a sector, right? So we're going to look at arc length and area of a sector, as opposed to and often confused with by myself as much as anyone, a segment of a circle, which is actually you make two segments with a chord, okay, and you make a minor segment. But that's a segment, right? Minor segment. This is a minor sector and a major sector. This is a major segment, right? We'll look at segment, how to find the area of a segment of a circle after we've done sector. But I just need to clarify what a sector and what the difference is between them. Okay, so the arc length and area of a sector. All right, so let's I'll get rid of this, make some space. Right. So let's start with a nice big circle, and right, let's look at a sector of that circle. Okay, now let's say that I've made this so that this is 3 centimeters, this radius, and I've made this angle here 1 radian. Now, from that information, you will know that this arc length here of this sector is 1 radius worth of arc length, because that's what a 1 radian angle does. It cuts off 1 radius on the circumference of the circle. So this will be equal to 3 centimeters here. All right, that's all very nice. And if I made this 2 radians, then it would be worth 2 of these 2 radiuses. It would be 6 centimeters. It would go out here somewhere. Okay, but to generalize, how about we go back and call this here theta, and this here r, and therefore this here will be r times theta, because this tells us how many radiuses there are. So r times theta in here. So that just gives us our first nice simple formula for the arc length of a sector. It's just r theta. L, this little L here, refers to arc length. You just use the lowercase l, and theta in radians, please. In radians, righto. So that's it. That's all there is to it. Example. All right, here's an example, nice and straightforward. Here's a circle. Let's say that I've got this angle here, which is 1.8 radians. 1.8 radians. There it is. 7 centimeter radius. All right, and the question is find the arc length. So the arc length is equal to, all right, let's get a different color out. The arc length, I know that this is 1. So what this tells me is that this angle has subtended or cut off 1.8 radiuses. So my arc length is r theta, which is 7 times 1.8. I've got 1.8 radiuses. So 1.8 times 7. All right, 1.8 times 7, without getting the calculator. Well, that's a division. What am I doing? 18 times 7. Why don't I just do 9 sevens and double it? 9, 7, 6, 3, 126, but it's 1.8, so it's 1 decimal place, so it's 12.6 centimeters. Does that look right? Does 12.6 centimeters there look sensible? If that's 7, and this angle's 1.8 radians, which is 1.8 radiuses, 7, yeah, just less than 2 radiuses, 12.6. Nice and easy, isn't it? Beauty of radians. Okay, let's look at a sector area. Let's look at the area of sector. So let's get another big blue circle out again and grab a sector of the circle. All right, now I want the area in here. Okay, my angle in here is theta. My radius is r. Right, let's work it out. My area, now you will have done these questions before in year 9, year 10, probably earlier, where you just worked out, well, how much of the circle do I have? Because I know my fraction of the circle is theta over 360, isn't it? And I know that my whole circle is pi r squared. So if I just take that fraction and multiply by pi squared, there's my area. Righto. The difference here is 360 is no longer. We're using 2 pi, aren't we? 2 pi is my, so this is in radians. So it's theta over 2 pi, which is my full rotation, times pi r squared. And the lovely thing here is, look at those pi's go. So we're left with theta r squared over 2, theta r squared over 2, or, as we like to write it, a half r squared theta. Look at that. Beautiful. So my sector area, sector area is equal to 1/2 r squared theta, r radius, theta in radians. Sector area equals 1/2 r squared theta. Up here, arc length equals r theta. A couple of really nice little formulas to use. We could do a little example here. So do an example. I find the area of find this area here. Right, so the question is, find area of sector. What have we got here? I've got 5 centimeters there. What have I got in terms of? This might be about 1.3 radians. 1.3 radians. So my area, let's work the area out. All right, it's 1/2 r squared times 25 theta 1.3. All right, so it's half of 12.25, so it's 12.5 by 1.3. Okay, I've worked that out to be 16.25. 16.25, just get rid of that, 16.25. 16.25 units, I haven't not specified, squared as my area there of that sector. Okay, finally, let's have a look at segment area. I want you to think about how we would find the area of a segment where we have a segment I just described to you is two segments of the circle, the major and the minor, are produced by a chord. That black chord there makes a minor segment and a major segment. So what we're looking for is this area in here. That's the segment area we're looking for. That's minor segment area. All right, how do we find it? Okay, maybe pause the video and come up with your own formula for r and theta there, because we know the sector area, and I reckon we know the triangle area. We can work it out. Go to it. Okay, now segment area, therefore, segment, as I just alluded to, I reckon is equal to the sector area minus this little triangle here, our triangle area. Okay, so sector area, using our formula, our sector area is half r squared theta. All right, going back up here, half r squared theta. That gives me all that there, all the way around the blue and the 2 red radii. That's my sector area. Now if I subtract in here, now this is a little triangle. Remember from the last section, the triangle with side lengths ABC and included angle theta. Remember we came up with the area being half AB sine theta. Now this gets you the area, what we're familiar with are right angle triangles, right, where we just go half base times height, half base height. But when it's not a right angle, we don't have any perpendicular height information, then we can use this. This was worked through in the last section, half AB sine theta. Now our AB in this case is RR, so it's not half AB sine theta, it's half R squared sine theta, where theta is that angle there, R squared. So that's the included angle between the two radii. So that's my segment area here, which we can conveniently rewrite, taking out a half R squared as the common factor, as a half R squared, theta minus sine theta, theta in radians. That's my segment area. Beautiful. So now 11L and 11M, they're all yours. I'll see you in class.